Natural Approach to Chemistry, Chapter 1, Section 2, Scientific Inquiry. When we hear the word chemistry, our minds typically conjure up images of colored liquids in various beakers and flasks. But really, chemistry is all around us. Where else might you find examples of chemistry? Is a plant growing an example of chemistry? Have you ever had random questions about the world around you? Questions like, how does soap clean? Where does plastic come from? Why do we even need sunscreens? Or maybe, why do we get hot when we work out? Why does fire transform wood to ashes, but ashes can't become wood again? In order to answer these questions, it's important to understand that the universe obeys a set of unwritten rules, which we call natural laws. Science is about making observations, collecting data, and creating explanations in order to discover what those natural laws are. Once we understand the natural laws, we can understand how the universe works and even predict expected outcomes. When we have a question like, why does smoke rise but rocks fall? We can approach these questions in a very systematic way. The entire scientific method of inquiry starts with questions, leads to a collection of evidence, from which we can arrive at theories. In your Lab 1A investigation, you are tasked with determining the possible internal structure of your observator. You needed to come up with a procedure for collecting observational information, such as listening for clicks or rolling sounds while keeping track of your observator rotations. Which two properties did your procedure need to have? Hopefully you remembered that all well-written procedures should be both objective and repeatable. Were your procedures objective enough to produce results that were useful when investigating other observators? Were your procedures repeatable and easily reproducible by other groups? When there are questions we seek to answer before collecting any data, we need to ask ourselves, can we make an educated guess as to what the answer is? You may make the educated guess that sugar dissolves faster in hot water. This educated guess is called a hypothesis. Now we would have something that we can test. In order to collect evidence that will help us answer our original question, we need to perform experiments. During experimentation, it is very important to record all of our results and observations. Even results that we think may not be related to our original question can later be crucial. A good rule of thumb is to record anything that is noticeable to you. Here is an example of an experimental setup. We see 3 different trials with 3 different amounts of sugar and 3 different amounts of water. We observe that all 3 trials resulted in different times for the sugar to dissolve. We see that the shortest amount of time recorded is in the hottest water. However, is this conclusively supportive of our hypothesis that sugar dissolves faster in hot water? The collected data might support our hypothesis, but there are other factors that vary between the trials as well. When we have several variables, it's difficult to tell which variable is affecting a measured result. In order to limit our variable to the one we're interested in, we should vary only the temperature between trials using the same amounts of sugar and water. Here we're going to change our experimental variable, but control other variables that we're not interested in. A variable is something that is measured or changed in a particular experiment. When we change only one variable at a time, we get specific data that will pertain to that particular variable. Here we have set up another experiment with only one variable whose amount we're changing. Each trial here uses the same amount of sugar and water, eliminating those as potential reasons for differences in results. When we are no longer varying those amounts, we call them control variables. Here, the controls are the amount of sugar, 5 grams in each setup, and the amount of water, 100 milliliters, again, in each setup. The variable that we are changing or testing is called the experimental variable. In this case, it's water temperature. Good investigations should have both control variables and experimental variables. Remember, the fewer the experimental variables at one time, the more clear your results will be. Evaluating the results of our second experiment, can we say that our hypothesis is supported and that sugar dissolves faster in hotter water? Now, because our experimental variable is temperature, we can say that yes, our results support our hypothesis. We're no longer concerned that the amount of sugar and the amount of water could have affected our results because those were kept the same between each trial. In review, a variable is a quantity that's measured or changed in an experiment or observation. The experimental variable is a single variable that is changed to test its effect, while the control variables are variables that are kept constant. Here's more data from another experiment. Where are the control variables here? We see that the temperature is kept relatively close to 25 degrees Celsius. And we see that the measured times are different from one another. Does this mean that the investigator made a mistake? There's always some amount of uncertainty in collecting measurements. We can't always have a perfect reading every time. We call this uncertainty error, but it doesn't mean that someone's made a mistake. This error is unavoidable difference between the real measurement and the unknown true value of the quantity being measured. Uncertainty or error is why we take multiple measurements for the same experiment, and then we'll average the results. Typically, we prefer to have many results to average because it lessens the impact of one bad data point. Taking the average also helps to improve the overall accuracy of an investigation. When we have multiple data points that we've averaged, we assume that the true value is the average. Here we see the difference between the measured time and the average in the first trial is 4.3 seconds. The biggest difference in the other direction we see in the second measured time, with a negative 3.7 second difference. We can see the estimated error, or difference between measurements and average value, is about plus or minus 4 seconds. Let's look at another set of trials. Here the question is, does sugar dissolve slower in warmer water? Two groups are collecting data. What are the control variables? What is the experimental variable? The largest difference between the data for group A and the average is 53 seconds minus 48.7 seconds, which gives us an estimated error of about plus or minus 4 seconds. Looking at group B, we see the largest difference between its average is 52 minus 49.3 seconds, or about plus or minus 3 seconds. When we compare the difference in results between groups, we see that group A has 48.7 seconds to dissolve in 25.5 degree water, while group B has 49.3 seconds to dissolve in 27.5 degree water. On the surface, it seems that sugar did dissolve slower in the warmer water, but let's look at how the estimated error can play into our results. The difference in times was only 0.6 seconds, and with the highest estimated error between the two groups of plus or minus 4 seconds, we see that this difference between the groups could just be part of unavoidable errors in reading measurements. What might be a better way to test the differences between dissolving rates in different temperatures? Remember that the scientific method of inquiry is cyclical. Once an experiment is over, we don't assume that potential conclusions are necessarily correct. New observations can always contribute to developing new hypotheses and generating new experiments. Sometimes, theories that have been widely accepted for decades or even centuries are proven incomplete or even incorrect. As we learn more, we adjust how we explain the world around us. Every theory is continually tested and retested, and results are compared and analyzed. This is how we move forward in our thinking. For hundreds of years, people truly believed that the Earth was the center of the solar system. The data that they had collected seemed to support this theory. Once Galileo developed the first telescope and began making observations that contradicted this original theory, he proposed that an Earth-centric theory was wrong. His data seemed to support a solar-centric system, which we now know is true. Just because a theory has been in place for a long time doesn't mean it can't be wrong. Key takeaways for this video are: investigation should be objective and repeatable. Variables are things we can change and measure in investigations. Keeping the number of experimental variables to 1 during a trial allows us to measure its specific effects on results collected. The scientific method of inquiry is cyclical and never-ending. There's always room for improvement.